All right, so this is going to be 5.4, part 2. So still vectors. In part 1, we talked about kind of the basic arithmetic. Well, we defined vectors. We talked about the basic arithmetic, scalar multiplication. In this video, we're going to talk about dot product, which is immensely important, not just for our class, but for future classes, especially physics classes, for example. And what it's going to be is it's a kind of product of two vectors, but as we'll soon see, it's not exactly like the idea of a product that we usually think of when we think of products. In this section, we'll also, at last, we'll talk about why cosine alpha plus beta is equal to cosine alpha cosine beta minus sine alpha sine beta. So we'll give an explanation for that using the ideas from this section. So once we've done that, right, in a way our class is very, very complete in that we've described all our formulas totally from scratch, right? Totally, you can reduce everything down to just a Pythagorean theorem. And, we actually know why the Pythagorean theorem is true as well. All right, so what's the dot product? So if I have two vectors, I can take their dot product, and the notation is a dot like that, all right? Never ever use the cross for product, so definitely do not do this. Well, first of all, you should never use the cross for products ever again in math anyway. If you are going to use something to denote product, you should use a dot. But in this case, you especially don't want to use the cross because there's also something called the cross product, which you might learn in the future, especially if you're going to be doing some sort of more advanced calculus. So we're not going to talk about the cross product at all. Maybe a little bit, but we definitely are not going to work with it in our class. I'll say a few words about it after we describe the dot product. Okay, so use the dot to describe the dot product. So just v dot w, all right? So actually that's oftentimes how we say the words or how we read this expression here. So v dot w, all right? So how do we actually do this thing? So luckily for us, the algebraic aspect of the dot product is really, really simple. So let's say v is equal to 3 comma 1 and w is equal to minus 2 comma 5. All right, then v dot w, the way you do it is, so let me write 3 comma 1 dot minus 2 comma 5, is you multiply the like terms. So 3 times minus 2, you multiply the 1 and the 5, all right? So what I'm going to get, 3 times minus 2, I'm going to have a 1 times a 5, right? And then what you do is you add them, all right? Okay, so ultimately this is going to be minus 6 plus 5, which is minus 1, all right? So one thing you'll notice that's very, very important is that this is a scalar, this is a number, right? So this is where the dot product is very different from what we usually think of as products, right? Because normally if I have 3, which is a number, and I have 5, which is a number, 3 times 5 is 15, which is also a number, right? But here I have v, which is a vector, I have w, which is a vector, but when I take the dot product of them, I get a scalar, all right? So be very aware of this, right? You're not ending up with a vector, you're ending up with a number. And that number has very, very important geometric geometric implications. All right, we'll talk about that in just a few minutes. So that's what I mean when I say the dot product is very different from what we usually think of as products. It's in a way unsatisfactory in that, right, the product of two things usually is, at least up to now in your math careers, the product of two things usually is another object of that same kind, right? But here it's a different type of object. Whereas, actually, if you do take more math and you talk about the cross product in the future, the cross product of two vectors is actually a vector, but it has its own unsatisfactory features. And one of them is that v cross w is not the same as w cross v, which is very, very bad. But you'll talk about that when you get to that in the future. However, with the dot product, we don't have that problem. W dot v is definitely the same because W dot v is minus 2 comma 5 dot 3 comma 1. And that's going to be minus 2 times 3 plus 5 times 1. Right, oops. Which is, of course, literally the same thing, right? Plus 5 comma 1, 5 times 1, right? Which is minus 6 plus 5, which is, again, the same thing. All right? Sorry, minus 1, which is the same thing. All right? Okay. So you might think it's kind of weird that we call this thing a product, but the reason it's called a product is because it satisfies all the usual properties that we think of when we think of the word multiplication, and in particular, this u dot v plus w, that's equal to u dot v plus u dot w. So the distributive law in particular is true. All right, and this I'll leave you to check for yourself. But this is definitely true, and this is essentially one of the main features of multiplication, right? That when you multiply one thing to the sum of two things, you can alternatively do that calculation by doing two multiplications first and then adding, right? Notice something really interesting here. This sum right there, that's the sum of vectors, right? This sum right there is not the sum of vectors. This is a sum of scalars, right? Because what happens is once you've taken u dot v and u dot w, those two are numbers. So this addition on the right-hand side is actually adding two numbers. Whereas on the left-hand side, this addition, you're adding v and w, which are addition of vectors, right? So while it looks simplistic, perhaps, this equation, it's actually a little more perhaps subtle than it might appear. Okay, of course, the same thing is true in the other. If I do it like this, u plus v on the other side dot w is certainly equal to u dot w plus v dot w as well. All right, and that's because as we said, the order doesn't matter for the dot product. All right, so so far it still feels a little weird because we have this strange definition of the product, right? We multiply the x coordinates or the x terms individually and the y terms individually, and we add them, right? Why such a strange thing? Why such a strange definition of the product, right? If I asked you, to define a product for vectors, if v was equal to minus 2 comma 5 and w were equal to 3 comma 1, maybe something you would naturally think of would be v times w, right, should be something like 3 times minus 2, which is minus 6, and then 5 times 1, and so minus 6 comma 5, right? But we did notice we did not define the dot product this way. And in fact, we don't ever define any product this way because all of this stuff, right, these products, these addition, subtraction, multiplication, scalar multiplication, are all defined because they're useful in real life or they're useful in some application. And it turns out what happens is if you try to define products in this way, just by multiplying the individual entries and then creating a vector out of those, that actually doesn't really have any real applications. It's not a natural way of multiplying things that gives you real life applications. But what happens is the dot product actually does have real applications and it does have actual meaning. And so that's why we have this strange definition for the product of two vectors. So let's talk about that meaning right now. So this is going to be the geometric aspect, or I guess I called it viewpoint last time, viewpoint. So a geometric viewpoint of the dot product. So what I'm going to do is I'm going to draw a picture and I figure out what exactly is the dot product calculating for us. So let's say I have a vector v like this, and let's say let's say this is in standard position, and so its coordinates are, or it's written as a1 comma a2. All right. Let's say we have another vector w, and let's say it's b1 comma b2. All right. Okay. Let's take a look at some of the quantities here. So this length right there, right? So this point right here is the origin, right? Because like I said, this is in standard position. And so the length of my vector is going to be square root a1 squared plus a2 squared, like we talked about earlier. So this length is square root a1 squared plus a2 squared. Okay. In the same way, this length here is square root b1 squared plus b2 squared. All right. Okay, let's actually fill in this guy right there. All right. Okay, so this guy right here, if I actually put a little arrow here, this guy is actually v minus w. All right, but we're not really that interested in that right now. Let me actually just give its length. Right, the length of this guy is going to be from the distance between 2 points, right? So the coordinate, let me do this in a different color here. So this one right here, because v is a1 comma a2, the coordinate of this point is a1 comma a2, right? The coordinate of this point is b1 comma b2. And so the distance between a1 comma a2 and b1 comma b2 is square root of a1 minus b1 whole thing squared minus a2 minus b2 whole thing squared. All right. So now we have the lengths of all three sides of this triangle. Okay, by the way, you could also get this formula from the fact that, again, this vector here, this blue vector, is v minus w. And so v minus w is a1 minus b1, comma a2 minus b2. And so the length of that is square root of a1 minus b1 squared. Sorry, plus, that's a plus. I don't know how a minus got in there. Plus a2 minus b2. All right. Okay, in any case, let me also talk about this angle here. So this is the angle between our original vectors v and w. Let me give that name theta here. All right. Now, one thing I want to note, whenever I draw two vectors with the same tail, like this and like this, there's always two angles that exist in this picture. There's this angle right there, and then there's the angle that goes all the way around like that. All right. So when we're working with vectors, we're always interested in the smaller of the two angles. All right. So when we say the words the angle between two vectors, we always mean the smaller of these two angles. All right. So that's just a baseline kind of standardization or notation. Okay, so this angle here, theta, is the angle between v and w. All right. I'm going to write down the law of cosines. So this is partially why we learned the law of cosines. So law of cosines says that relates. Let me do this in a different color here. So it relates this length squared in terms of the other two lengths squared and that angle on the opposite side. right? So let's write that down. So this length squared, so luckily for us, right, we're going to be talking about the square of all these lengths. And so this length squared, actually the square root goes away. So I have a1 minus b1 squared plus a2 minus b2 squared, all right, is equal to the length of the first one squared. So that, again, the square root goes away. So a1 squared plus a2 squared. And then the second one, b1 squared plus b2 squared, right? So let me put parentheses like this. Okay, so let me give these some names just to relate it more to our law of cosines that we talked about in the past. Let me call this guy, if I call this guy C, I call this length A, and I call this length B, right? Then we would be saying that C squared, so this guy here is C squared, is equal to A squared plus B squared, right? And then we're going to have more terms, right? Minus 2 times the length of, again, 2 times A times B, and then cosine theta, all right? Okay, I'm writing A and B here because I actually don't need to write out the A1 and B, A1, A2, B1, B2, because actually what I'm going to do is I'm going to interpret A and B here, right, as actually the lengths of V and W, right? So if we go back up here, this A square root A1 squared plus A2 squared, it was the length of of V, right? So this A right here is the length of V, okay? And this B over here, in the same way, that's the length of W, right? Okay, so I'm actually gonna keep it like this, all right? What's interesting here is actually this left-hand side, I can just brutally just multiply it out, right? So this left-hand side is A1 squared minus 2A1B1 plus B1 squared. That's the first term. And then the second term is plus A2 squared minus 2A2B2 plus B2 squared. All right. Okay, now why did I do this? Well, what happens is I have an A1 here on the left-hand side, A1 squared on the left-hand side. I have one on the right-hand side. So they're going to cancel. I have an A2 squared on the left-hand side. Let me use a box for that. And I have an A2 squared on the right-hand side. They're going to cancel. Okay. I have a B1 squared on the left-hand side. I have a B1 squared on the right-hand side. They're going to cancel. And I have a B2 squared on the left-hand side, and I have a B2 squared on the right-hand side. They're going to cancel. Okay, so a lot of these guys actually cancel out, and what I end up with is minus 2A1B1 minus 2A2B2 is equal to minus 2, and I'm going to rewrite this as VW, length of these guys, cosine theta. All right. Okay, now I also have minus 2 on this side, minus 2 on this side, minus 2 on this side. So those minus 2's actually cancel. So I end up with A1B1 plus A2B2 equals length of V, length of W, cos theta. All right. Okay, but what's A1B1, A2B2? Well, remember, V was A1 comma A2. W was B1 comma B2. So this so V dot W is what? A1B1 plus A2B2. So this left-hand side right there is actually nothing more than V dot W. All right. So this discussion here tells me that V dot W algebraically, we have it kind of that as its computation, but we can also write it as V dot W is length of V, length of W, cosine theta, where again, the picture is if this is V and if that's W and that's theta, right? Theta is the angle between them, right? The smaller of the two angles between them. So this is a geometric description of the meaning of the dot product, all right? It's the length of one vector times the length of the second vector times the angle between them, All right. And in a way, in many ways, the right way to think of this is that the dot product tells you about the angle, right? Because in a lot of circumstances, the angle is the thing that's hard to calculate. Lengths are easy, right? You just use square roots, right, and stuff like that, and you got the length. But the angles are hard to calculate. So in a way, and also notice this, the dot product is easy to calculate as well, right? Just from up here, a1, b1, a2, b2. So if you look at this equality here, everything is easy to calculate except for except for the theta, right? So in a lot of circumstances, the way we're going to think of dot products, or perhaps you in the future, is going to be like this, right? So now the way you should think of this is the right-hand side is easy to compute, right? Whereas this guy is hard. And so the dot product essentially tells you about the angle. All right. So in particular, I can be even more specific here. Theta is equal to arc cosine of v dot w over length of v, length of w. All right. Okay. So this actually gives us a very nice application of simple application of the dot product, right? If I have v is 3 comma 1, w is 2 comma minus 3. Let me use a different number, 2 comma minus 5, right? Then what's the angle between them? What is angle between v and w, right? How would you figure this out? You could draw v, v is 3 spaces and then 1 space, 3 spaces right, 1 space up. W is 2 spaces right and 5 spaces down. And then you could maybe do some trig to figure it out, right? But that's not necessarily easy. However, if I understand this formula above, right, this relationship between the dot product and the angle, then I instantly get it. Theta is equal to arc cosine of v dot w, and that's easy. 3 times 2 is 6, plus 1 times minus 5, so 6 minus 5, over, right? So top is a dot product. Let me write it in 2 steps. V dot w over length of v, length of w, right? So I just calculated v dot w was 3 times 2 plus 1 times minus 5, which is minus 1, positive 1. And then what's the length of v? It's 3 squared plus 1 squared, square root. So this is going to be square root of 3 squared plus 1 squared, which is root 10. And what about w? It's going to be square root 2 squared plus 5 squared. So that's going to be square root minus 5 squared, actually. But the minus sign goes away. So it's going to be 29, right? And so ultimately, I get a very simple theta is equal to arc cosine of 1 over root 10 times root 29. All right. Okay, and then of course, if you actually want the theta, you can plug it into a calculator and you've got the actual radians or degrees, whatever, of theta. Okay, so you don't have to do any kind of drawing or any sort of geometry. You actually have a formula for the angle instantaneously in a way, right? And what I mean by that again is that, right? Look at what kind of math I needed to do this right-hand side. I just needed to add and do a square root, right? I need to add, multiply, do a square root. And up here, I just needed to add and multiply, right? So this right-hand side, I can't stress enough that this right-hand side is so easy to compute, right? That it allows us to understand the angle theta really, really easily. Okay. Next. Now this is still kind of unpleasant, this arc cosine, right? We hate arc cosines and stuff like that. So actually, one use of the dot product is this. Notice if I have v dot w, this is 0, right? What does this mean? How could this possibly happen? Well, v dot w, if we look above again, is equal to length of v, length of w, cosine theta, right? So if I know v dot w is 0, what's the implication of that in terms of um, geometry, right? Well, if v dot w is 0, so let me say if v dot w is 0, then that means 0 is equal to this. So then let me write it like this, that this is equal to 0, right? Which means that either either the length v is equal to the 0 vector, or w is the 0 vector, or cosine theta is equal to 0. All right. Because if v is the 0 vector, that length of v is 0. If w is a 0 vector, length of w is 0. And of course, if cosine theta is 0, then this whole thing is 0. Okay, so that means that if I know v and w are actual vectors, non-zero vectors, then that means cosine theta has to be 0. So if v, w, not 0 vector, right, then cosine theta has to be 0. All right, but how can cosine theta be 0? Cosine looks like this. Cosine theta is 0 is right there, right? And of course, it's only this one and not this one or any of the other ones. We only are interested in this one because the angle between two vectors, right, we're taking the smaller of the two angles, and the smaller of the two angles has to be less than 180 degrees. And so we're only looking at cosine from here to there, right? And the only place cosine can be 0 from here to there is at that point right there, which is, of course, at pi over 2. Okay, so what that means is theta is equal to pi over 2, right? And what is theta equal to pi over 2? Pi over 2 is 90 degrees, right? And so we can conclude if v dot w is equal to 0, then, and v and w are non-zero vectors. So if they're not the 0 vector, because if they were 0 vector, then it's kind of silly even to talk about this. Then they're perpendicular. V is perpendicular to W. And there's another word we use for perpendicular, which is orthogonal. Orthogonal to W. All right. So the picture is, of course, V might look like this, W might look like this, and the important feature is that the angle between them is 90 degrees. All right. So this is super, super powerful because it allows us to figure out when two vectors are perpendicular without having to do much work, right? So if I give you v is equal to 3, 1, and w is equal to minus 2, 6, and I ask you, are they perpendicular, right? V perpendicular to w, question mark, right? So this means perpendicular to right? Are they perpendicular? Well, all you have to do is take v dot w and see if you get 0, right? So this is going to be 3 times minus 2, which is minus 6, plus 1 times 6, which is 6, equals 0. So yes. All right. Whereas if v were equal to 4, 5, and w were minus 1, 2, right? V perpendicular to w, well, I just calculate v dot w, and I get minus 4 plus 10, which is 6, so the answer is no. All right. So you don't have to do any math at all, pretty much, right? You only have to know how to add and multiply. And you can figure out, a pretty advanced question, right? Are these two guys perpendicular? Just think about how you would do this before today. How would you have done this? You would probably have to kind of think about, v as this vector here, w as this vector here, and then somehow you'd have to figure out that angle, right? But at this point, you know that you just have to take their dot product, and you instantaneously have your answer. Okay, so this is actually maybe the most important, one of the two most important features of the dot product, right? So you'll see homework problems where you're asked to compute the actual angle between two vectors, and you're going to want to use this arc cosine business here, or sorry, up here, right? But in reality, uh, probably the majority of the time, you're going to be using working with dot products and considering angles is going to be considering whether the angles are perpendicular or not. And that's because perpendicularity or orthogonality is very important in real life. It allows you to break hard problems down into easier problems. Um, and one very important application in our real lives, day-to-day lives, is in compression. So when you want to compress whatever, a piece of music, a video, anything, one of the main ideas behind compression is to use this idea of projection. And the idea of projection, we'll actually talk about this in the next section. This idea of projection involves orthogonality. All right. So this was perpendicularity. Before we actually talk about how to tell whether two vectors are, so whenever you talk about perpendicular, right, there's also the concept of parallel, right? In the past, perhaps you talked about two lines being perpendicular and two lines being parallel. So they often go together. So in 1 second, we're going to talk about how to tell whether two vectors are parallel. But before you do that, let me just note that if you do take more advanced mathematics, one thing that's really cool is you'll have objects, mathematical objects that you can think of as vectors in a way. So actually, after you take second semester calculus, you can even understand what I'm going to say right here. We can work with functions, and we can think of a function as a vector. So you can define the dot product of two functions. You can define the length of a function, right? And if you can define these two concepts, then you can take f of x dot g of x and divide it by length of f, length of g, right? And notice that I'm completely mirroring the mirroring this v dot w over length of v, length of w, right? So in the vector setting, this is equal to cosine of theta, right? So in the kind of more advanced settings, you can actually define the concept of the angle between two functions using this idea here. All right. So once you've defined the idea of a dot product of two functions, which you can do very easily actually, once you've defined the idea of the length of a function, which you can do very easily, then you have the concept of what it means for two functions to be to have an angle between them, right? You can talk about the angle between two functions, and even more importantly, you can talk about two functions being perpendicular, and that's actually where this idea of compression can be used, because functions can represent, for example, an image, right? So just in the most simple sense, right? An image consists of, brightness. So here's bright, dark, very bright, less dark, right? So this would represent an image, and then using functions representing images, you can use this idea of perpendicularity to do compression. Right? Maybe this is a silly example. Maybe think of it like this. Right? Each of these. So if you have an actual photographic image, right? Let's just make our lives simpler, black and white, right? So you can represent an object, right, by this grid, and inside the grid are different values, right? Maybe a large value for white, a low value for darker, for black, right? And this can be represented as a function, right? So at every point here, you have a value of its brightness, and so that allows you to do compression. Okay, we can't really go into this too much because we can't talk about the actual dot product or the length without calculus. All right, so that's just somewhat something to look forward to in the future. All right, let's talk about parallel. So when are two vectors parallel? So r v equals 3 comma 1 and w equals, let's say, 12 comma 4 parallel. Let's make our lives more interesting. Let's say minus 12 and minus 4. Okay. All right. So first of all, what do we even mean by the word parallel in the context of vectors? So in terms of the picture, what we mean is they point either in the same direction, literally the same direction. So both of these kind of point, northeast or something like that, or in the direct opposite direction. Okay. So all these three vectors that I've drawn, they're all considered parallel to each other. All right. Um, we have this definition in terms of pictures. What does it mean in terms of kind of the algebra? Well, two vectors are parallel, so v and w are parallel if v is equal to, if one of them is a multiple, let me write like this in words. If one is a constant multiple of the other. Okay. All right, so what that would mean is that v is equal to, for example, 4 times w, or w is equal to minus 3 times v. All right, so that would mean that they're parallel. Okay, so to determine whether two vectors are parallel, when you're given their kind of coordinates like this, you just have to solve an algebra problem, 3 comma 1 equals c times minus 12 comma minus 4, right? Two vectors are parallel if one of them, right here, 3 comma 1, is a constant multiple, c, of the other. Here's the other guy, right, w. So if we can solve, so if there is a solution to this problem, then they're parallel. All right? Otherwise, they're not. Okay? So it boils completely down to algebra, right? Are they constant multiples? Well, 3 comma 1, is this equals c times this? Can we solve this? Well, this right-hand side is minus 12c comma minus 4c. And for these two to be equal, that means 3 has to be minus 12c, and 1 has to be equal to minus 4c, right? So what we do is we solve this. 3 equals minus 12c, 1 equals minus 4c. The way this is structured, we can get c from the first equation. C is equal to 3 over minus 12, which is minus a quarter. And then we have to check, does that work for this second equation, right? So, or you can solve the second equation and see if you get the same answer, right? Let's just do it by checking. So I plug minus 1/4 in for c. So plug minus 1/4 in for c here and see if equation is true. Right? If it's true, then the answer is yes, we are parallel. Right? If we get something which is not true, then they're not parallel. So let's check it. 1 equals minus 4 times minus a quarter. That's equal to, minuses cancel, 4's cancel, equals 1. Looks like we're okay. All right. Okay. On the other hand, if I had, let's say, 3 comma 4 and 5 comma 7, right? So let me write are these two guys parallel? If I tried to do this, right, 3 comma 4 equals c, 5 comma 7. This would be 5c comma 7c. So I would be solving for 3 equals 5c and 4 equals 7c. Okay. This first one gives me c equals 3/5, right? But if I plug c equals 3/5 into here, gives 4 equals 7 times 3/5, which is 21 over 5, right? So these two are definitely not equal, right? 20 over 5 is 4, but 21 over 5 is definitely not 4. and so not parallel. Okay. All right. So checking parallel is relatively easy as well. But again, it's the perpendicularity, the dot product, that's actually more important. But you will see a few problems like this on the on this homework. By the way, notice the general principle here. We have two equations and we have one unknown c. So in general, there's going to be no solutions, right? So that's what we saw here, right? There's no solutions to this problem because 4 was not equal to 21 over 5. And so they're not parallel. And so what that kind of tells you in general is that it's very hard for two vectors to be parallel, right? If you just close your eyes and randomly pick two vectors, they're generically not going to be parallel because for them to be parallel, the two equations and one unknown has to match up perfectly with each other. All right, and that makes sense, right? If you literally close your eyes and draw two vectors, right, they're almost certainly not going to be parallel to each other. Okay, so the last kind of official part of this section before we talk about our cosine alpha plus beta is just a bit of notation. So first of all, unit vectors. So a unit vector, oops. So unit, U-N-I-T. So whenever you see the word unit, that refers basically to 1, all right, to the number 1. So a unit vector is a vector of length 1. So any vector of length 1 is called a unit vector, all right? So 1 over root 2, comma 1 over root 2, this guy is a unit vector. All right. Why? Well, because its length, let me call this v, right? Because length of v is 1 over root 2 squared plus 1 over root 2 squared, which is 1/2 plus 1/2, which is 1. Okay. On the other hand, w equals 1 comma 2 is not a unit vector because length of w is 1 squared plus 2 squared square root, which is root 5, right? Not equal to 1. So not unit. All right. Unit vectors are really, really important because oftentimes you're only interested in the direction of a vector and not really its length. So so in that context, right, you don't really want to work with vectors of length 3 or length 1/2 because you're just complicating things, right? Where vectors of length 1 are very simple. So in those situations, you very frequently would like to work with unit vectors. So one thing you frequently want to do is if you start out with a vector, just a random vector, let's say this one up here, w equals 1 comma 2, right? So it would look, so the picture for that would be 1 step right, 2 steps up. So w literally looks like this, right? So the question is, if I have a regular vector like this that's not a unit vector, can I create a unit vector out of it, right? Can I create a vector that's in the same direction, but is a unit vector, right? And again, we very, very frequently want to do this. And we'll see this in the next section. How do I do that? Well, luckily for us, it's really, really easy. W over its own length, that's always a unit vector. All right. If you take a vector and you divide by its own length, then you always get a unit vector. Of course, with the exception of if you have the 0 vector, but obviously you can't do it in that case. So in this case, oh, by the way, what does it mean when I write w divided by length of w? Length of w is a number, right? What do I mean by divide? Well, that actually means w times 1 over scalar multiplication, right? So this is scalar mult. Right? Because technically, in a way, this guy, we haven't really defined it because I never defined for you scalar division. But just like subtraction doesn't really exist, division also doesn't really exist because you can always phrase division in terms of multiplication, right? So instead of dividing by this number, you're multiplying by 1 over that number. Okay, so of course we're often lazy and we use this shorthand of division, even though literally this guy is what we technically mean. Sorry. Okay, so what is that? Well, that's equal to 1 over length of w. We've already calculated that. That's root 5. And then we scalar multiplication that with 1 comma 2. How do we do that? Well, just regular scalar multiplication. That ends up being 1 over root 5, comma 2 over root 5. Okay. So this guy here is a unit vector. Unit vector. And very importantly, it's a unit vector that retains the direction of w, right? All it did was change the length of it to be length 1, which again, we very, very, very much like. Okay, and you can always check, right? Let's calculate the length of this. This is 1 over root 5 squared plus 2 over root 5 squared. So we get 1/5 plus 4/5, which is 5/5, which is 1, right? And so, of course, when I square root both sides, I'm going to get 1. All right. So one thing that there's two very important unit vectors in our class because we're primarily working in the plane, and that's going to be the unit vector that's 1 comma 0, that direction, right? The horizontal vector that's length 1, and then there's also a vertical vector that's length 1, 0 comma 1. All right, so these guys are so important that we give them names. This one is I, and the way we write it is I. Instead of writing a dot for the I, you put the arrow on top. And this one is J. Instead of writing J with a dot, you put J with the arrow on top. Okay, so these are important because any other vector can be written in terms of I and J, right? 3 comma 5 is actually 3 times 1 comma 0 plus 5 times 0 comma 1. And so that's actually 3i plus 5j. Okay, so any vector can be written in terms of I and j, right? In terms of these kind of more basic vectors, these unit vectors, horizontal and vertical, right? Okay, so we're not going to be using these guys too much in our class, but it's very standard notation. And if you will be working with vectors in the future in calculus or in physics, you'll certainly be using this kind of notation. By the way, one way to phrase this is we've written the vector 3 comma 5 as a linear combination of I and j. All right, so this is a linear combination of I and j. Okay. What linear combination means is we're taking I and j and we're multiplying numbers to them, 3 and 5, and we're adding them or subtracting them. Okay, so very simple in our situation, but the term linear combination is really important. And if you do take more calculus or calculus in the future, you'll definitely hear that term in 3rd or 4th semester calculus. All right, so we'll use both notations. So the 3 comma 5 with the sharp brackets, and also the 3i plus 5j notation as well. Okay, so finally, let's at last talk about why this guy is true. Right? So in the past, when we gave you this sum formula, we didn't explain it. We said we would explain it later, and now is that later. All right? And we can do it now. So we could have done it before, right? We had in a way, the mathematical knowledge to do it before, but it wouldn't have been very motivated. But right now when we do it, it's going to be relatively simple. So very, in a way, elegant. Okay, so the way I'm going to do this is like this. I'm going to draw a vector of length 1, all right, and where this angle here is alpha, all right. I'm going to draw another vector also of length 1, and so this is where you can see unit vectors are nice. We'll see that this length 1 helps us a little bit, makes our lives a little easier. So this guy's also of length 1, and this angle here will be beta. All right. So for example, if cosine, if we're adding cosine alpha 30 degrees plus 45 degrees, then we would have this angle would be 30 degrees, and that angle here would be 45 degrees. Okay. Notice I'm not thinking of this as a negative angle. I'm only measuring a positive angle here of 45 degrees. Okay. All right. In this setting, this vector here has a head, right? I'm gonna call this head, the coordinates of this head, A1. Sorry, I guess I should just write it as a vector, right? A1, A2, and I'm gonna call this one here B1, B2. Okay, so the A's with the alphas, the B's with the betas. Okay, let me write out our dot product formula that we just learned. So it said that A dot B. So let me actually scroll up. Oh, sorry, I didn't want to use A and B, but let's scroll up and I want to emphasize literally the one we talked about earlier, right? So V dot W, let me find it up here. Right? V dot W is length of V, length of W, cosine theta. All right? So let me use that. So I do have two vectors. I guess I should give them names. So let me call this capital O. Let me call this capital A. Let me call this one capital B. Okay, so A dot B is length of A, length of B, cosine of the angle between the two vectors, right? But the way I've cleverly set this up is the angle between the two vectors is alpha plus beta. All right. Okay, and I've also cleverly set this up so that the length of A and the length of B were 1. So this is actually just cosine of alpha plus beta. All right. Okay, now what I'm going to do is I'm just going to calculate this left-hand side, and essentially the formula that we want will just pop out immediately. All right, so what's A dot B? A dot B is, well, the coordinates of A is A1, A2, so that's A1, A2, and then B is B1, B2, so B1, B2, dot product, right? And so that's just going to be A1, B1 plus A2, B2. Okay. All right, now let's look at what A1, B1, A2, and B2 are. So let me just draw A right here. So this was my vector A. It was A1 comma A2, right? This is length 1. What that means is this length right there is A1. Let me do that in a different color. So this one right there is A1. That one right there is A2. Okay. All right. Also, remember this angle here is alpha, right? Okay. Now, if we look at this setup, of course, I've dropped a right triangle here. And so cosine of alpha is adjacent A1 over hypotenuse over 1, which is just A1. Sine of alpha is equal to A2 over 1, which is just A2, right? So actually A1 and A2 turn out to be just cosine alpha and sine alpha, right? So in our expression down here, A1, that's just cosine of alpha. A2, that's just sine of alpha. All right. Okay, B1, B2. So this one is a little more subtle. So this was our angle beta, right? This B is equal to B1 comma B2. And the way I've drawn this, right, I've set this up so that B is pointing in the in the fourth quadrant, right? So B1 is a positive number, b2 is a negative number, right? Because it's in the negative y. It's below the x-axis, right? So it's negative. So actually, when I talk about lengths of this right triangle, so I'm dropping the same right triangle again. When I talk about the lengths of these sides, this length here is going to be b1. And this length here, right, b2 is negative. So to make that positive, this is minus b2. Okay. All right. So let's write down the sines and cosines, just like we did for the a. So that was my a computation. Cosine of beta is adjacent over hypotenuse. So b1 over, and again, this is a unit vector. So b1 over 1, which is b1, right? So up here, this b1 term is cosine of beta. All right. Okay, what about sine? Sine of beta is opposite, which is minus b2, right? And again, we needed that minus to make, because b2 was negative, over 1, which is minus b2. And so this last term here, b2, is minus of sine beta. All right. Now, if we put all those together, what do we have? Well, on the right-hand side, we had cosine alpha plus beta. And that ultimately was equal to this guy here, right? So let me write that again down here. That's cosine of alpha plus beta is equal to cosine alpha, cosine beta, right? That's the first one here, next one here. And then we have a minus sign right there, right? This is a product. So we have minus sine alpha, sine beta. Okay, and that's it. That was the formula that we had a few sections ago for adding cosine of the sum of two angles. All right, and again, now that we have this idea of the dot product, it's actually very easily explained. All right, and I guess I should also remind you, right? The reason this formula was true, this a dot b is length of a, length of b, cosine alpha plus beta. The reason that was true was from the law of cosines, right? So again, law of cosines, I want to emphasize, is something that we actually do use outside the context of kind of solving triangles. All right, and again, from here we got cosine of alpha minus beta, right? From here we got sine of alpha plus beta. From here we got sine of alpha minus beta. From here we got tangent of alpha plus beta. Dot, 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 all of the other ones, right? From these, we got cosine of 2 alpha, right? From these, we got cosine of 1/2 alpha. From these, we also had sine of 2 alpha. From these, we had sine of 1/2 alpha, right? So all of these ultimately come from this, and this ultimately, we can see it as coming from what we're talking about today, the idea of the dot product and vectors. Okay. So that'll be it for this section. Next section, we're actually going to use all of this technology of vectors for some simple applications, kind of physics applications. But again, I really highly emphasize that you use this in many more circumstances than just the simple ones we see in our class. This is enormously important in math and physics. And actually, these days, AI is really a big deal, right? It's one of the hot topics. And one of the ways to kind of work AI is using vectors. You think of your neurons as a big vector, and then you work with them in that way. Of course, in that context, you're working with vectors. Our vectors only have 2 entries, right? 1, 3. But if you want to go to 3D, right, to model real motion, 1, 3, 5, this would be x, y, and that would describe z. And in terms of AI and stuff like that, you would work with vectors that have hundreds and hundreds possibly of entries. Okay, but ultimately they're still vectors. The properties that we've talked about still hold. Even the dot product still works, right? The dot product of this would be 2, 4, 6. Dot product would be 1 times 2, plus 3 times 4, and then you would add plus 5 times 6, right? So everything actually extends very well to higher dimensions and more complicated settings. So uh, this section here is actually really, really important um, in general.